Dear students, in our previous lecture, uh, we discussed necessary conditions for a complex function to be differentiable at a point. Naturally, we must now be looking for sufficient conditions. However, before taking that up, we shall equip ourselves with an important mathematical tool known as Taylor's series, which is a very important not only in mathematics but also in physics, computer science, and engineering. We start with developing an intuition for this series using physics and geometry. Now, coming to the point, consider the following graph. Look at this graph. We have a function, a real function of one single variable. Fx is a real function. We will later on extend Taylor series to complex functions that which is of course included in our syllabus. Now fx is a real function of single variable and x is plotted here. Take this form of the function first. Suppose the function is like this. Okay, constant function. That means its value does not change with x. Now if I select 2 points, two values of x, say a value here and another value, which this a will be fixed, but the other value that I may adjust, I can change that. So this other value, let me call it by denote it by x itself. So what is the value of function at a? Of course it is fa. And what is the value of function at x? It is fx. As you can see, both the values are equal. So we can write, for this special function, we can write fx is equal to fa. New value is equal to previous value, the old value or the previous value, whatever you like to call them. Okay, so simple. This is analogous to a particle, a car at rest. Suppose you have this is a road and there is a car here. It is at rest. It is not moving. It is at rest, and there is an observer here, and the observer is looking at the car. The car is at a distance of 5 meters from the observer. This distance is called position of the car. We say that position of the car is 5 meters. And if the car remains there, its position will not change. It will remain at a distance of 5 meters from O. So this will be its position will remain constant. You can think of this as position of the car or the distance at which the car lies from the observer. Now in this case, if we take this, make this more concrete and take this as an example fx, then here fx is ft, because time is changing, and with time, right now it is not ft, of course, because the car is in rest, so nothing is changing. Time is of course changing, but the distance is not changing. But when we let the car move, then we will have ft as distance. That means we can write ft for distance, because distance is function of time. Distance will change. Distance covered by the car as the car moves, that will change with the time. Okay, then in place of fx we have ft. So x, we will identify x with t. It is as if the time. Nice. Now fx of course is the distance. Fx is distance. We will think of this as distance. This will help us in understanding certain things that I'm going to discuss. Now next is suppose now fx changes with x, and if we allow fx to change, we have two choices. We can let fx change, but in such a way that rate of change of fx is constant. This means that fx will change at a constant rate. Then there is another choice, fx will change at a variable rate. Let me show it here by this graph. Suppose fx is constant up to this value of x, say a, up to a, fx is constant. This is fx. Okay, and then fx starts changing, but starts changing, but at a constant rate. You can see constant rate. Now, this fx now, in case of if we now translate it into motion, then this graph would mean that your car is at rest up to this time. Say up to 2 seconds, it is at rest. Let this be 2 seconds. After 2 seconds, it is at rest. It doesn't move. Its distance from the observer remains constant up to that. But at the end of the second, it starts to move. But when it starts to move, of course, distance will change. This S will change. That means Ft will change. This is Ft. Ft will change, but Ft changes in a linear way, uniformly. That means motion, speed of the car will be uniform, constant. Distance will change in a uniform way. Okay, this is then the other possibility. We started with this constant fx, and then now we are using, here is an fx that is changing, but changing in a linear way. Now I ask a question to you. This is the original value of fx. Okay, now the question is, take this other point x, and now at x, what is the value of fx? Fx, actually, at a, what is the value of fx? Fa, right? Now, are the two now equal? No, not at all. The two were equal here because it was not changing. Its slope was 0. Now the two are changed. This fx is changing. Of course, it is changing at a constant rate. That means it has a slope but a constant slope. It has a derivative but a constant derivative. Now, when fx is changing, fx is not equal to fa. In that case, fx is greater than fa. Of course, greater than fa. But how much greater? Yes, this much. This much. Let me denote this point by p. This point is p, and this is m. So pm is the amount by which fx is greater than fa, because at this point value is equal to fa, this fa point. Now this much is the additional distance covered because of the this increasing this because of the velocity, because of the motion, uniform motion. Oh, okay. How much can we calculate how much this is? Easily. How? If we are given rate of change of this fx, if we know how fast fx changes, we can easily calculate it. How? Let me show it. This change, I can first, let me write fx is equal to, this fx is equal to fa plus change in fx. Change in fx is this. This is delta fx. Okay. Change in fx. Now, how much is change in fx? Quite easy to see. It is we can write it here. Let me write it here. Fx is equal to fa plus change in fx. Change in fx can be written as rate of change of fx with x into change in x, delta x, change in x delta x. Now how is this true? Because we just need to realize that df by dx means change in the function, change in fx per unit change in x, per unit change in x, per unit change in x. In fact, why we call it rate of change? Simply because of this unit denominator. This is change in fx per unit change. Why unit change? Because denominator can always be cancelled with this. It can cancel. It can be cancelled, and it can be reduced to a unit 1 by cancellation of factors, common factors. Now, suppose for example you have you can yourself then You can easily understand this. Now this is simply change in function per unit change in x, but the total amount of change, the total change in x is not unit change from this point to this point. The change in x is x minus a. X minus a is the change in x. Now since x minus a is the change in x, I can then do this thing. I can write fx is equal to fa plus change in I will denote this by f dash x means derivative of fx with respect to, you can read it as f dash x or f prime x. Now we will be using dash f dash x into change in x, that is x minus a. Change in x is x minus a. So this is change in function. This is change in function. This and this are same. Change in function dfx means change in function per unit change in x, multiplied by the total change in x. That will give you total change in function. It is something like this. Cost of one book is this, say 10 rupees. Cost of one book is 10 rupees. What is the total cost if I purchase 4 books? 10 books, cost of one book multiplied by 4, that gives you this. I hope this is clear to you. Now after this, let us go to another case now. So this far we have studied this case. Initially we were having this is x here and this is fx. Initially we had fx and x we had it like this, horizontal line without any this change in fx. So line number 1, then we had this linearly changing fx. Now suppose fx is not linearly changing, it is changing in a non-linear way like this. This is the third case. First case, second case, third case. Let me summarize this here in this table. Curve, then for this curve, for a particular curve, what is fx? Okay. What is f dash x? Okay. What is f double dash x? F double dash x, that is second order derivative. Let us see. Curve number 1. For curve number 1, fx is constant. Say c, constant. C stands for constant. Fx is constant. F dash x, what is it? F dash x means rate of change of fx, that is 0. When it's constant, its rate of change is 0. And what is rate of change of f dash x? That also is 0 because it doesn't change. Now in a curve number 2, or curve number 2, this you have fx variable. We will write v stands for variable. Curve number 2, fx is variable. That means distance is changing. If we translate it into distance, the distance is changing with time. This time here, and then next f dash x is changing. F dash x, no, it is not changing, it is constant. This is changing variable, this is constant, and this definitely will be 0 because it is rate of change of this which is constant. That means rate of change of this fx here for this curve is constant. Fx is not constant, its rate of change is constant, it is changing uniformly. And the third curve, this here we have for the third curve we have fx variable, f dash x also variable, its rate of change is changing. Now rate of change is changing, and finally this, but its rate of change is changing in such a way that rate of change of the rate of change is constant. That means let it change at a constant rate. In order to explain this graph, you need just to consider a uniformly accelerated motion. Here is uniformly accelerated motion. Uniformly accelerated motion. A simple example that I will offer so that it is quite clear for you. This graph, this table is clear for you. It is something like this. Suppose we have this situation here. In this table I am showing you different instants of time, and in this table I am showing you distance, or what I call ft, fx, ft, where x means t. Okay, distance is equal to fx. Now in this column I will show you velocity. Velocity is equal to f dash t. Since velocity and variable, the symbol is used for both or similar, so I will change this. I will call it var, variable, var. Okay. Now f dash x, velocity is rate of change of distance. Then I have acceleration, that is rate of change of acceleration is rate of change of this f dash x, rate of change of velocity. That means it is rate of change of f dash x, that is f double dash x. Okay. Now 0 time, suppose at 0 time the car was at rest, so it is at a distance of 5 meters from the observer, and at the end of first second it is again at the distance of 5 meters. It is not moving. At the end of second it is again at the distance 5 meters. It is not moving. But right at the end of second, it now begins to move. Since it begins to move, its position will change. Its position, that means its distance will change. At the end of the third second, suppose it has covered a distance of 8 meters. It is at a distance of 8, not covered 8 meters. It is covered only 3 meters in this. In this second, it is covered 3 meters only. But since it was already at a distance of 5 meters from the observer, hence total distance that it is from the observer is 8 meters. Now at the end of 4, let it be 4. This is 11 meters. How much distance did it cover in first second? 3. In second 3. And in next interval again 3. That means fx is changing. That means ft is changing. Ft is changing. Okay, but changing at a constant rate. If that is the case, then if it is changing at a constant rate, it is not represented by this third. It is represented by 2. This and this second. Let's first show this thing. Then it is 14 meter. Now what is rate? It is rate of change. Since it is now changing, hence it is rate of change is not 0. Of course it is 0 here. It is 0 here. It is 0 up to this, because it's not moving up to till the end of the second. It is not moving. Now from second onwards it is moving. Now here it is not 0 now, and this at the end of the second, its speed is 3 meter per second. Now just a minute. Sorry, I have pressed perhaps this 3 meter. 3. Now 3 meter. So not 3 meter. It is 0 meter, 3 meter per second. Let me explain it in order to avoid any sort of confusion. The car begins to move at the end of the second. As it begins to move, it moves with a constant. We will imagine it moves with a constant speed, right from this onwards, and the speed with which it moves is, let it be 3 meter per second, because in next second it is going to cover 3 meter. So I say that its speed here is 3 meter per second. You may wonder how it can attain 3 meter per second speed without taking any time. Let's ignore those things in order to extract our desired this information from this. We can imagine that the acceleration at this point was so huge that the time that it took can be neglected easily, and hence abruptly it then started with a speed of 3 meters per second. Okay, now with this thing it continues then with the same speed here, with the same speed here, with the same speed here, and as a result you can see its rate of change from this to this. We will consider only this much of the graph, this much. Rather, I should do one thing here. I should have drawn it like this. Suppose this is the second. This is this second. Prior to second, the graph was this. Position is constant. Always think that fx in our example means distance. Fx means distance. This is fx, distance. Now, then onwards, distance changes, position changes, and it changes linearly. It changes 5 to 8 to 11 to 14 linearly. Whatever is rate of change, its rate of change is constant. That means f dash x is constant. Look, now it explains this curve number 2. This was curve number 2. For curve number 1, everything is okay. It is simple. But for curve number 2, fx means distance. Let me write it, distance. This means velocity. This means acceleration. Now fx, what is the distance? Distance is variable. In curve number 2, distance is variable. Distance is changing. Of course, from second. We will be discussing mostly. We will confine our discussion to this. From second to fifth second. Now at the end of the fifth second. Now we have variable distance, variable velocity constant, and acceleration 0. Of course, when velocity is constant, acceleration is the rate of change of velocity, that is 0. So this explains curve number 2, and this also explains why distance traveled, for example, at the end of this, say at the end of this, why that should be this distance traveled, this distance traveled, why should be equal to distance traveled at the end of the second. That means f x, this is x, or you can think of this x as fifth second. F x is equal to fa, this much is fa plus this distance. This distance is traveled because of this velocity. That means now from velocity, if you want distance, you will have to multiply the velocity with time. Velocity into time is distance. So velocity, this is velocity, but it's f dash x. Velocity into time, which time? This time, the elapsed time, this time, from second to fifth second. Now how many seconds are there? From second to fifth, 5 minus 2, that is 3. If we multiply this by 3, I will simply write it x minus a. This explains this equation. Now comes the last, that is uniformly accelerated. It was previously, it was not uniformly accelerated. We should write not uniform motion. That was uniform, although we had the intention of explaining uniformly accelerated motion, but somehow we landed into this. We thought it proper to first have a look at this. Now let us go back to this uniformly accelerated motion. This will explain everything and certain interesting things. Accelerated motion. Okay, uniformly accelerated motion. We have the table. First, let us show the table here. In this table, as usual, we will be showing time, distance, or fx is the same as fx, and then we have velocity or f dash x. This is how physics imports meaning to mathematics. Now acceleration, it makes understanding mathematics so simple. Acceleration f double dash x. That means acceleration is rate of change of velocity. Okay, now 0, 1 second, 2 seconds, 3 seconds, 4, 5, 6, and at beginning, it was the core was at a distance of 5 meter from the observer, again at a distance of 5 meter, again at a distance of 5 meter, and then core started moving. It then covered a distance of 3 meter in first second. That was so the total distance covered will be 8 meter. Then it covered in first second it covered a distance of 3 meter. In next second, let us make it cover 5 meter, so that velocity is not uniform now. So if it covers now 5 meter, 8 plus 5, that's 13. So it must be at a distance of 13 meter away from the observer. Then 3 here, 5 here, 7 here, that will be 7, that is 20 meter. Look what is happening to its distance now. 7, 3 here, 5 here, 7 here, 9 must be here, that is 29 meter. What about velocity? You can check, that is 0, 0, and right at the end of this it began to move. So initially its velocity was 3 meter per second, then its velocity is at 5 meter per second, because in next second it covers 5 meter. In next second it covers say 7 meter. How many? 7, yes, 7 meter per second speed. In next it covers this, yes, of course. In next it covers 9 meter per second. Enough. Okay, you can see yourself that velocity is no more constant. F dash x is not constant now, it is changing. But thank God it is changing, but at a constant rate. Look at its rate of change, 2, 2, and 2, changing but at a constant rate of change. That this means that its acceleration is constant. Acceleration is 0, 0, and now it is constant from this onward. In first second it accelerates from 3 meter per second to 5. That means its acceleration is 2 meter per second square, 2 meter per second square. And then it is again from this to this, it accelerates by 2 meter. So 2 meter per second square, 2 meter per second square, 2 meter per second square, and so on. Okay, now good. If we draw the graphs, here are the graphs. Now this is x means time, and this is fx means position or distance covered by the vehicle, by the car. Okay, now you have here say 1, 2, 3, 4, 5, 6, 7, 8, etc. This at up to second the car was at rest, and then it started moving. It started moving. Now this is the, but when it started moving, it did not now move at constant rate. So the graph will not be this straight line. Graph will rather be this. We say that this curve has curvature. Curvature means departure from straight line direction. Suppose there is a line like this, and then suddenly it starts departing from this straight line departure. This, now we say that there is curvature. Now similarly, there is another thing. If a line leaves a straight line path, we say it has curvature. If it leaves the plane, suppose it rises above the plane of the screen, then we say it has this torsion. That's called torsion. Anyhow, that's not our topic. Okay, now see, for this curve, let us first write which are, yes, here is the that table of curve, and then this is curve, then this is fx, distance traveled, f dash x, velocity, f double dash x, acceleration. Curve number 2, I mean this curve initially, this was curve number 2, which has a constant rate of change of fx. Curve number 2, this was curve number 1. Curve number 1 has, let us first write curve number 1. Curve number 1, this is curve number 1. In curve number 1 we have first fx fx constant is constant, f dash x 0, I mean for this, f double dash x 0, column number 2, fx variable, is var variable, f dash x is constant, that is velocity is constant, speed is constant, acceleration is 0, of course. And in curve number 3, which is our main focus now, that is in curve number 3 we have this fx variable you can see change, f dash x, that too is now variable, but one thing is constant, that is rate of change of f dash x, that is constant. Let's assume this constant. Of course, then after this case there will be a case in which this will be variable, this will be variable, acceleration will also be variable, acceleration will no more be constant, it will be variable. That too is a case, but after discussing this case we will learn a lot, our vision will be broadened, and we can then forecast what will happen if all the three are variable, what happens then. For that matter, we need not go for this detailed analysis, it will be quite easy for that, but here this is our that moment of serious thought. Here we have to develop an expression for fx, we have to see what now fx, that means let us do this thing, this is a, this is our x here, and this is what I am looking for, this is our fx. Now what is the relation between fx and fa, that means distance traveled at the end of this interval, how is that distance related to distance at the beginning, at the start of the interval? Of course, one thing that I can see, this distance, this total distance covered by this car is that can be written as in three parts. One part of it is f equal to fa. First part is equal to fa. Second part, this much is equal to, we have already calculated that, and if we take this much, this change in fx, or the total, for example, by total I mean this total, because of this constant speed, distance traveled, total distance traveled because of this constant speed that we have already developed, that is equal to fx is equal to fa plus f dash x into x minus a, f dash x into x minus a. This gives us this much distance up to this point. Now the important thing is that this additional distance, that is our concern here, this additional distance. Let me simply call this additional distance delta s, delta fx. Let's say delta fx. How much is this delta fx? That is our point. To understand how much that this delta fx is, let us go to this situation. Let us deal here with another situation. That is, see, I draw this graph once again. This is the graph. This is x. This is fx. Okay, and this is a, as you know, a, and then let us first draw our this constant case, then this uniform case, then lastly our this non-uniform case, and see, this is x. Okay, this is the situation. The question is, how can we measure this distance? Of course, initially, when you had this case, second case, when you were dealing with second case, how did you measure this distance? there what we did, we multiplied rate of change of fx, that means f dash x, by this interval x minus a. That was what we did in order to find this much of distance, rate of change of fx into x minus a. Perhaps you would be tempted to say that, sir, we can do the same thing here. In order to measure this distance, this much of distance, let us multiply f double dash x, rate of change of this fx, rate of change, the second rate of change of f dash x, because now this f dash x is changing. Here in this case, in case number 2, fx was changing, fx. In case number 1, fx is not changing. In case number 2, fx was changing. When fx was changing, the change of distance you got by multiplying this f dash x, rate of change of fx with x minus 1. When f dash x itself is changing, then naturally, like this, you would use second order derivative, and multiply that by x minus a. To make this point completely clear, let us look at this table. Case number 1, this is case or curve number 1. Okay, what was changing in curve number 1? In curve number 1, fx was changing. Fx was not fx was constant. So was f dash x 0, its rate of change 0, and rate of change of this 0. Okay, that was also 0. Okay, in curve number 2, fx was variable and f dash x was constant. And how did we, and how, this additional, in curve number 2, how did we get this additional distance? This additional distance we got by taking rate of change of this, rate of change of this is but this, by taking this rate of change of this, multiplying that by time interval, the x minus a, multiplying that time by interval. Can we do the same here in third case? Can we do the same here? Say for example, we have this variable, again variable, this is now variable, but one thing is there, it is rate of change is constant. It's rate of, can we do this thing now? See, look at this case, and then copy this case here. In this case, what we did, let us write the expression here. In this case, what we did, we took f dash x and multiplied that by x minus a to get the additional distance, not the total distance. For total distance you will have to add fa to it. That means fa to it. Then that will give us, I am talking right now, I'm sorry, I lost this perhaps. No, it is here, thank God. Now fa is here. I'm talking only about this additional distance. Similarly, what will be the additional distance? This additional distance, naturally you would say that, well sir, it will be f double dash x. Just like here, it was f dash x multiplied by x minus a. In this case, it must be f double dash x multiplied by x minus a, f double dash x multiplied by x minus a, but that is impossible. Why? Because f double dash x is acceleration. This is acceleration, and this is time interval. Acceleration to time is not distance, it is velocity. Acceleration to time is not distance, it is velocity. Previously it was velocity. It was velocity into distance, into time. Velocity into time. That is distance. Now we have acceleration into time. That is velocity, not distance. What we have to do? We have to convert this change into distance change. That means we have to convert at into distance, not into velocity. As you have seen, this is change in velocity. Which change in velocity? Yes, that is to be seen, and that is very interesting. This change in velocity. This is the velocity acquired by the body because of the acceleration. This is in addition to its uniform velocity. It would have if it had no this acceleration. Let us go back to this table in order to understand it. It is something like this. Let me first clear some space for it. It is something like this. If we do one thing, this velocity, let us do one thing. We break this velocity into two components, two parts, velocity into two parts. This is, of course, these two I will not consider. I will go from this. Now, what is the velocity here? 3 meters per second. Here 5 meters per second. Here 7. Here 9. Okay. Now, if I do one thing, first I ask myself, what is the maximum common velocity that they have? Maximum common velocity, that's of course 3 meters per second. Let me write that first. 3 meters per second. Here velocity, I am breaking this velocity, that means 3 meters per second into 3 meters per second. Okay. Then what about this? 3 meters per second. 3 meters per second. 3 meters per second is everywhere. But this has something in addition to 3 meters per second. Now write that additional part. That is 2 meters per second. Additional part. What is the additional part here? 0 meter per second. Here 2 meters per second. What is additional part here? 5 meters. This is 7 meters per second. When you take out 3 meters per second from it, you get 4 meters per second. Now then you have 9 minus 2, 9 minus 3, 6 meters per second. These are the velocities due to acceleration. That is because these velocities are because the body is accelerated, the car is accelerated. This velocity is the velocity if the motion of the car had not been accelerated. When motion of the car is not accelerated, this motion is represented by this. That means the distance, this much distance covered by the body is because of this constant acceleration. Because of constant acceleration. What you are looking for? You are looking for this distance which has covered because of this varying acceleration, varying velocity. Okay. Now that will be equal to this. That will be equal to this. That additional distance that it covers. But how much will be that additional distance? Let's see. Since it does not have same velocity at the beginning or at the end. At the beginning its velocity is 0. Velocity 0 means in terms of these derivatives we can say at the beginning f dash x is equal to 0. At the end f dash x is 6 meters per second here, but we can write it in another way. Say this in this particular example is 6 meters. I'm not going to use 6 meters here. I need a general formula. Now see how can I have a general formula. See, since f dash x is constant, f dash x is constant here. Now f dash x is constant. Not in this case. F dash x is not constant. It is f double dash x is constant. F double dash x is constant. Okay. Here f double dash x is constant. Okay. That means rate of change. See what I want. I want what will be the, first let me formulate the problem. My problem is that I want what will be the velocity. This velocity, I want what will be this velocity at the end of the interval, that's here. Velocity here. Now I know, if I know rate of change of velocity, I can figure out what will be the velocity at the end of this interval. Rate of change of velocity is this. What does that rate of change of velocity mean? It means that this is dear rate of change of velocity. The acceleration, the rate of change of velocity. Now rate of change of velocity means how much velocity changes per second. Per second, velocity change per second. What in order to get total change in velocity, what I need by cross multiplication, you can see dv total velocity, total change in velocity that I need is f double dash x into dt. Simply integrate it, you will get change in velocity. That total change in velocity, which I denote by delta v, will be equal to that will be equal to, since this is constant, acceleration is constant, hence it will be taken out of integral. So f double dash x into total interval delta t. So what is then to f double dash? It is the f double dash x, f double dash x, f double dash x, okay, into delta t. Delta t is x minus a, x minus a. So what is the total change? That means what is the total velocity at the end of the interval? That is f double dash x into x minus a. Let me once again tell you that this is change in velocity due per unit change in time, change in velocity per second into number of seconds. That means total change in velocity. That means this total change in velocity. Okay. Now, now what is the change in velocity here? 0. What is the change in velocity here? This much. Change in velocity is here f double dash x into x minus a. This means change in velocity here is 0. Change in velocity is here this. That is this. How much distance will this car travel because of these additional velocities, these velocities? How much distance? Yes, we can easily calculate that by multiplying velocity by the time interval. But which velocity? This or this? The average. Let's take average of these two extreme velocities. Average at the beginning of the interval velocity is 0. At the end of the interval velocity is this. So average will be their sum of this plus this, sum of these plus this divided by 2. So I write here now average velocity will be velocity at the end of the interval, that as you saw, that is f double dash x into interval x minus a plus that is there, it was here f double dash x into x minus a, then and it is 0 here, 0 here plus 0 divided by 2. You are taking average of this, that is average velocity is equal to f double dash x into x minus a divided by 2 Okay. Therefore, how much distance, additional distance, it will travel because of this average velocity? That's quite easy now. Additional distance delta s, that means this additional distance, this additional distance. This additional distance delta s will be equal, distance is equal to velocity into time, that is average velocity into time. Time is x minus a. So when I substitute it here, I get this average velocity f double dash x by 2 into x minus a. This much is average velocity. Now average, after having substitute average velocity, you know this is you have just substituted value of v bar, average velocity. You have not substituted here, you have not included this much here. Now multiply this by the interval x minus a. Once again, f double dash x divided by 2 into x minus a is average velocity into time interval. So what we get, additional distance is this is the additional distance. Additional distance is then delta s is equal to, let's go to previous page. Additional distance is f double dash a by 2, f double dash a by 2. Okay, once again we go back and see what it is. Sorry, f double dash a by 2. Then we have okay, f double dash a by 2 into x minus a into x minus a. That is delta s is equal to f double dash a by 2 x minus a whole squared. Therefore, total distance fx will be equal to fa due to constant, this constant position, initial constant position, plus one more factor due to that f dash x into x minus a plus f double dash a divided by 2 into x minus a whole square. Now, I will change one thing here. This f dash x is, it is constant here. F dash x in this term constant. So I can take its value anywhere. Let me take its value at a. So fx will be equal to fa plus f dash a into ax minus a plus this term f double dash a by 2 x minus a square. Now we are now ready to finish this lecture. Now, before finishing it, suppose now f double dash x also changes. Suppose now f double dash x also changes. That means if you go back to our previous page, you have f double dash x also changing. That is where was the table? Yes, f double dash x is constant here. Now suppose it also changes. Suppose acceleration is not constant. Rather, here acceleration is 2, here 3, here 4, here 5. So acceleration will be changing. But then acceleration has two parts. One a constant part, 2, 2, 2, 2. Another a variable part, 1. But thank God, rate of change of acceleration is constant. Rate of change of acceleration is constant. Now in that case, and since acceleration is not 0 now, rate of change of acceleration is not 0, it is constant. This rate of change of acceleration is also given a name. It is called jerk. So jerk is constant. Then what we will do, first we will calculate the total acceleration, that total change in acceleration, change just as we did calculate total change in velocity, we will calculate total change in acceleration by including f triple x and something and time interval. And then from that total change in acceleration, we will then go to total change in velocity. From total change in velocity, we will translate that into the distance, equivalent distance traveled. So if we continue with that, we will get terms like this. You must have seen the trend, the pattern. Now let me do one thing here. I will put 1 here. Now 1, 2, and then if you include other terms, in that case, if you include other terms, then the next term turns out to be f triple dot a, and that is third this derivative, third order derivative, but it now is this factorial. It is not 2, simply it's 2 into 3. You can check it, you can try, stretch your imagination and try to get it on the basis of same arguments that I used. You can do it. It is not difficult. You can do it, but it takes a little bit of time. Now, of course, we are going to give you rigorous proof of all this, but proof has its own this place, while as this concept is very, very important. Now, what do you then conclude? This is what, my dear, you can then include more and more terms, and you will get an infinite series. We call that Taylor series. This is the Taylor series. This is what you call Taylor series. It has infinite terms. Then there is one more thing that is called Taylor's formula. If you just stop somewhere, stop at the end of a certain number of terms, we then say that it is Taylor's formula. And Taylor's formula is basically an approximation. That, of course, is an approximation because you are dropping out certain terms. So my dear, let us now just look at what we found. We found that any function fx, of course this any needs to be qualified a little bit. Fx is equal to fa, it is original value at a point, plus then f dash a into x minus a plus f double dash a divided by 2 into x minus a squared plus similarly f triple dash a divided by 3 factorial x minus a whole cube plus dash dash plus dash dash, something like this. This is called Taylor's theorem. What is important, Taylor's this series, what is important, what is most important is that this Taylor's series needs that the function fx should be infinitely differentiable. That means we should be able to differentiate it once, then also differentiate, take second order derivative, then take third order derivative, then take fourth order derivative. We say that it must be infinitely differentiable. In sum, of course, at a point, say a point, what is point A, it must be infinitely differentiable at a point. Then why this, when we say at a point, it means something. It means, for example, if you want a function to be differentiable at a point, it means simply that it must be definable in, it is at least in some neighborhood of that point. Because in order to find a derivative of a function at a point, you need to include some of the neighborhood of that point. We will discuss these things in detail, but after we give a geometrical this interpretation of this Taylor's theorem. I hope till we come up with a geometrical interpretation, that is geometrical interpretation much simpler than this, but then this is also must, because the moment you write these terms now, you must have a feel what these terms represent. Try to infuse these meaning into these symbols. One of the physicists, Brian Cox, his famous statement that I remember, he says that every mathematical equation is a story in itself. It is a story in itself, a movie in itself. So, my dear students, I hope that this Taylor's theorem, this is, sorry, I am saying Taylor's theorem and Taylor's theorem, Taylor's series is that is now to some extent comprehensible to you, plausible. I try to make it as much plausible as possible. Thank you.